We're in Chapter 7, Section 7.5. In this section, we'll determine the logarithmic function that best approximates the data, and we'll answer questions on logarithmic regression. Now, we've did this before with other functions in previous chapters, and now we're going to do it for logarithmic functions. So, in previous chapters, we've looked at the characteristics of a linear, quadratic, cubic, and an exponential function. And now in Chapter 7, we've looked at logarithmic functions. Before, in previous chapters, we've looked at linear, quadratic, cubic, and exponential regression. And we answered questions based on the characteristics of the regression. We will do the same now in this section for logarithmic regression. So we've looked at linear regression, quadratic regression, cubic, and exponential, and we're going to add now logarithmic regression. You won't be asked how to or what type of regression is used. You will be given what type of regression is used, so you won't have to determine that, but you will need to know the characteristics of each type of function. So if you recall, the line of best fit is a straight line that best approximates the trend in a scatter plot. The curve of best fit is a curve that best approximates the trend in a scatter plot. To interpolate is a process used to estimate a value within the domain of a set of data based on the trend. To extrapolate is a process used to estimate the value outside the domain of a set of data based on the trend. So logarithmic regression is the constant plus the multiplier times ln x. Most technology will represent the logarithmic equation as a plus b log x. So when you're doing regression, this is how you will see it show up on your calculator. You'll be given an a and a b value. So let's jump right into an example. The population of Alberta as a function of time can be approximated by a logarithmic regression function. And you'll have to answer questions such as the ones here. First of all, is the function an increasing or decreasing function? And we can see that the function is an increasing function. We could also be asked the domain and range. And the domain in this case, since we're talking about population and people, we must have more than 0. So the population will be greater than or equal to 0, but the population will also be natural numbers belonging to a set. We cannot do a set of real since we cannot have half a person in population. In this case, the range, its years sits the 1900s. So once again, the range, years, I'll say, is greater than or equal to 0. So we have years. What year did the population exceed 2.5 million? If we look at the graph and estimate, 2.5 million is here. What year did they exceed? You could say, based on the trend, it might be around 89, somewhere between 85 and 90 years. Okay? But it's giving us the logarithmic regression function right here. So we could put 2.5 million in here for p and determine time. So that would give us time would equal -346.090 plus 28.957 times ln of 2,500,000. This would give us, when we put it on our calculator, the time would be 80.5 years. What year will the population exceed 3.5 million? So once again, we could look at the graph and extrapolate based on the trend. It could be somewhere between 110 and 120 years after 1990. That's when that would be. So we can use the graph, or we could put it in for p as well. Here's another example. We have, it says the age, t in years, of an ancient object is a logarithmic function of percent of carbon-14 remaining in the object. So here is the logarithmic regression function. It is a decreasing function. And it says if 96.8% is present, what is the object's age? And so we could put 96.8 in for p the percent. So the age would be 38,070.332, subtract 8266.961 ln of 96.8. And when we do that, that'll give us 268.4. And so you could see that when it gets 96%, which is somewhere in here, that yes, it's possible for it to be 268 years old. Another question we can consider is the domain of the object. The domain, of course, because it's percent, will be between 0 and 100. And so if it's between 0 and 100, it could also be from a set of real numbers. When you're looking at the range of the object, of course, the age in years will never be negative, and so our range will be greater than 0, greater than or equal to 0. Once again, for regression, you will be expected to answer questions using a graph of a regression. You will be expected to substitute values into a regression function. Once again, you'll be given the type of regression. This is very important. You will not have to determine what type of regression is there. And you will be able to be expected to answer questions on the characteristics of the function type of regression. So if they say it's an exponential regression, you'll have to recall the characteristics of an exponential function. If it tells you that it's a logarithmic regression function, then you'll have to answer questions based on those characteristics.